Okay, guys, welcome to Unit 3 Periodic Trends. So, first in this unit, we're going to learn about Coulomb's Law, which is basically how we explain a lot of periodic trends. Then, we're going to look at our first trend, which is atomic radius. And next, we will learn a bit about electron configuration, which is basically how you write about the number of electrons of a certain atom. And lastly, we are going to learn about ionization energy, which is another trend. So before we get into it, let's review a little bit. So an atom has a nucleus made up of protons and neutrons, and this nucleus has rings of electrons around it. These rings of electrons can also be called electron shells, and the number of electron shells increases as you go down the periodic table. The outermost electron shell, which is what is over here, is called the valence shell or valence shell. Either one's fine. And the electrons in the valence shell are called valence electrons. So now let's get into our lesson. So as we discussed earlier, protons have a positive charge and electrons have a negative charge. So think of these two particles as a pole of a magnet. We know that opposite charges will attract and like charges will repel. And similarly to if you ever held two magnets together, you'll know that as you bring them closer and closer, it's harder to push them together, right? Let's say I have one magnet and I'm holding the south end to the south end of another magnet and I'm trying to push them closer and closer and it gets harder to try to touch together. So this is what we can imagine about protons and electrons. Protons in the nucleus will attract electrons and electrons in electron shells will repel each other. And Coulomb's law is basically saying, part of it at least, is that the closer two charges are, the stronger the force between them is. So that could either be a attractive force or a repulsion force. And this force between two charged particles, such as two magnets or a proton and an electron, is called an electrostatic force. So here we have the equation for Coulomb's law. First, F over here represents the electrostatic force, which is the repulsion or attractive force. Here, K is a constant, so it's just a number that stays the same, and it's not too relevant right now to our understanding, so let's just ignore that for now. Then we have Q1 and Q2, which represent the charges of our particles. So Q1 could be a proton or an electron, Q2 could be a proton and an electron. And then now down here we have R, which represents the distance between the two particles Q1 and Q2. So we can kind of see that representation here. And in here, in this diagram on the right, Q1 is a proton and Q2 is an electron. So they're attracted to each other, but if Q2 was also positive, was also a proton, the force would be repelling each other. So according to Coulomb's law, in an atom, if there are more protons, there is a stronger pull on electrons, and there is a stronger force of attraction. And we can see that in this equation. As Q1 increases, F will also increase, right? And if we have more electron shells, that means that there's a greater distance between the proton and electrons. And so there's a weaker force of attraction. And so we can also see that here. If R increases, then F will decrease. So now let's get into our first trend. Atomic radius is measured by putting two atoms of the same element side by side, then measuring the distance between their two nuclei and dividing that distance by 2 to get the atomic radius. So here's an example with hydrogen. We have two hydrogen atoms lined up right next to each other. They're touching over here. And we just assume the nucleus is right here. So we measure this distance between the two nuclei and divide it by 2, and that is how we got the atomic radius of hydrogen. So here is a table to kind of see how the trend for atomic radius is. So as you go to the right, atomic radius will decrease. And as you go down, atomic radius will decrease. It will increase, sorry. And so now let's learn why. So as you go across, like I said, atomic radius will decrease. And this is because as you're going across, you're getting more protons. So if you have a periodic table on hand, which it's good to have, let's look at the second row, carbon and nitrogen. We can see that carbon has 6 protons, nitrogen has 7 protons. So since nitrogen has more protons, there are more protons to attract the valence electrons, or your outermost electrons. So that means there's a stronger pull on them, and they're pulled closer to the nucleus, which reduces the distance from the nucleus to your outermost electrons, which decreases your atomic radius. And as you go down the periodic table, the atomic radius increases. This is because when you're getting more shells, you're getting a larger atomic radius because you're basically increasing your distance. You're just increasing your radius. Pretty self-explanatory. Okay, and now we are going to get into electron configuration. This can get really complicated really quickly, so if you have any questions, you should ask your teacher. You can email us. But yeah, don't get too frustrated if you're not getting it immediately. So electron shells can also be called energy levels. That's just another name for them. And each energy level can have sublevels. And there are 4 sublevels that are labeled S, P, D, and F. Just labeled letters. And each sublevel has a certain number of orbitals, and each orbital can hold 2 electrons. So let's break down each sublevel. First, we have S, which can hold 2 electrons because it has 1 orbital. And S starts on energy level number 1. So that means that the elements, helium and hydrogen, which are on row number 1, both have S sublevel. Next, we have P, which can hold 6 electrons because it has 3 orbitals, and this starts at energy level 2. So once your S sublevels in your P in your second energy level are filled up, electrons start going into the P sublevel. Next, we have D, which can hold 10 electrons and has 5 orbitals. And this starts at energy level 3. And then lastly, we have the F sublevel, which can hold, sorry, this is a typo over here, but this will be fixed soon, which can hold 14 electrons and has 7 orbitals. And it starts at energy level 4. So D and F get really complicated really quickly. So for most of your middle school and some maybe your high school career, you're not going to go very much in depth about D and F. So don't get too concerned about those right now. So here's just another table to kind of clear it up. I would just be repeating what I said in the last slide, but you can pause the video and look at this table by yourself. So now we are going to learn how to write electron configurations. So this is, a lot of people will use the periodic table to write electron configurations. There is another method, but this one is the most preferable. Okay, so your electron configuration, this is how you're going to write it. So first, you're going to write the energy level. So that's going to be 1 or 2 or 3 or 4. Then you're going to write your sublevel, which is, remember, that's S, P, D, and F. So let's see. And then lastly, you're going to write the number of electrons as a superscript. So here we have nitrogen as an example. Nitrogen, in its neutral atom form, has 7 electrons. So first, we're going to start on energy level number 1. And I said that S starts on energy level 1, right? So we're going to go 1s2, because it has 2 electrons in the first sublevel. And then we go down to go up to energy level 2. So we go 2s2, and then we go to, so now both of your S sublevels have been filled up, so now we go to P, which starts on the second sublevel. So we get 2p3. And so if you add these numbers up, 2 plus 2 plus 3 is 7, and that is how many electrons nitrogen has. Okay. And you can also do this looking at your periodic table. So this is what we had earlier. So nitrogen would be over here. So if you wanted to do with your periodic table, you could do 1s1, 1s2, and you're going down to 2, 2s1, 2s2, 2p1, 2p2, 2p3, and that is what we got over here. And electron configurations are hard, guys, so don't get too frustrated. We will go more in depth with them on our next chemistry course. Will be like intermediate or advanced chemistry. But for now, just knowing that there are sublevels and energy levels is good enough. Okay, so let's review a little bit. Energy electron shells can also be called energy levels, and each energy level has sublevels. These sublevels are called S, P, D, and F. Each kind of sublevel has a different number of orbitals, and each orbital can hold 2 electrons. Okay, so let's get to our last part of this lesson, which is ionization energy. So ionization energy, let's just look at the word for a minute. The first 3 letters are ion, aka ion. So ionization energy is the energy needed to remove a valence electron from an atom, aka ionizing your atom, because you're removing an electron. Okay. And then this is also measured in kilojoules per mole. So we can see here you have a neutral lithium atom, which is the nucleus. There should be one shell over here for its 2 inner electrons, and then has 1 valence electron. And once you take away that valence electron, you're left with lithium plus, which is now its charge, and you have an electron. So the more valence electrons an atom has, the harder it is to remove an electron. And so ionization energy increases going across the periodic table. Well, not exactly, actually. So we actually want to look at Coulomb's law to explain ionization energy again. So you remember earlier I said that having more protons would increase the electrostatic force, right? The attractive force on the electrons. So as you're going to across the periodic table, you're increasing the number of protons. And so that means that the pull on your outermost electrons, on your valence electrons, gets stronger and stronger. And that's why it gets harder to remove an electron, because the attractive force between the outer electrons and the nucleus is stronger. So this slide will be fixed after this recording. But yeah. And so you might notice, you might also say that, look, like atomic radius also decreases as you go across the periodic table. Does that mean that ionization energy is increasing because your distance is decreasing? And the answer is no. You cannot use another trend one trend to explain another trend. So you're always going to want to use Coulomb's law to explain your periodic trends. Okay. And then as you go down the periodic table, it becomes easier to remove an electron because your number of energy levels is increasing. So that means the distance is increasing and your electrostatic force gets weaker. So it gets easier to remove an electron. Okay, well, that concludes Unit 3. Thank you so much for listening. If you have any questions, feel free to email us or ask your teacher or search it up. Yeah, thank you for listening to me.